Yeah, please. Okay, so today, this afternoon, I'm going to talk about frequency redistribution, and that sounds a bit undescriptive, but what it means is that I will talk about, I think after this lecture, we should have quantitative understanding of this particular process, right? Why the scattering proceeds in the way that is shown in this cartoon. So, yeah, frequency redistribution, a very short topic. So, I'll talk about Lyman-alpha radiative transfer as an, not a differential, but an integral differential equation. And this is what makes, the problem so complicated. We've actually talked about the most of the emission processes already. And today I'll focus exclusively on the scattering term. Right? And specifically I'll talk about frequency redistribution and how it depends on direction, which is not often realized. And I'll talk about three properties of frequency redistribution which allow us to understand Lyman-alpha scattering basically and quantitatively very well. Right? So that's quite a lot to promise. So basic radiative transfer equation that you often see in textbooks is just given by this, right? It's the change of intensity of a beam propagating in some direction n across a path length ds. Is just proportional to the opacity times the intensity, and you add an emissivity term to that. Right? So that's the basic radiative transfer equation you often see in books. Right? And what we're going to do instead now is, I'm not going to work in ordinary frequency units, new here. I'm going to work in this dimensionless frequency unit x. And we've seen this already in I think, in X's lecture again. Right? And also, I'm not going to care at the moment for this discussion about the directional dependence of the radiation field. It's going to be, we're just going to assume it's the same in all directions. Right? And for Lyman-alpha, you can imagine that this might actually be reasonable because photons scatter many, many times. So if you're on a particular location in space, it's actually the same in all directions, right? Irrespective of where you look. Right? So for the sake of the rest of the discussion, we're going to drop the directional dependence of the radiation field, which is going to be fine. Right, and the other thing, right, I guess that's it. Right, so when you do that, and I think the equation should drop. Yeah, here it is. Right, the equation simplifies to something like this. Now, the angle average intensity is denoted usually with J, right? Not I, but J. So you have dJ ds equals minus alpha J plus little j. Right, and alpha would just be the opacity. Right, and the opacity has units of per length, right? So it has the number density, in our case, of hydrogen atoms. This is the hydrogen atoms are what can absorb Lyman-alpha photons, right? So we care about the number density of hydrogen atoms times the absorption cross-section. And this is what we discussed this morning, what this cross-section looks like, right? So we looked at the functional form of this absorption cross-section, right? And we plotted it in the final slide of this morning's lecture. It had this weird, this Lorentzian type of profile. Right? So that's what we talked about this morning. We've already, in the second lecture, we talked about this particular term in the radiative transfer equation, and we know how to compute it. Right? This is coming from recombination and collisional excitations. These are the two processes that give us Lyman-alpha. And just to emphasize, fluorescence, we talked about that as well yesterday, but fluorescence is still, you power the emission through recombination. So it's really just recombination and collisional excitation that always give us this term. So we can compute this one, we can compute this one. Right? However, all that this equation has in it is emission mechanisms and absorption. Right? There's no scattering in this equation whatsoever. Right? Oh, before I come to the scattering, just want to make one simplification which is common in the literature and which you've also, if you take a radiative transfer class, you've seen, or if you will in the future, you will see. And that's when you make one simplification in which you introduce this quantity called the optical depth and the source function. Right? And we hear about the optical depth, we've heard about it many times. I mentioned it this morning that the optical depth of the interstellar medium, for example, to Lyman-alpha is about 1 million or 100 million. So I've mentioned it before. Right? So you introduce the optical depth, which is just defined as basically alpha times ds. Right? So you bring this to the other side. Right? Right, in any case, what you then get is you get dj d tau equals this minus phi, and phi is now just to give you the shape of the absorption length profile. It's not the cross-section itself, it's just the shape of the cross-section. You have minus phi times j plus this quantity s, which is the source function. So what the main modification we have to make for Lyman-alpha, which it gives us all the problems, is this new term, the scattering term, and that's given here. Right? And the reason it has this particular form is that we are interested in computing the radiation at some frequency x. Now what scattering does, what it does, it can actually bring photons from different frequencies x prime into frequency x. Right? And that's encoded in this term here. So we know that there's photons at other frequencies x prime. We know that these photons can scatter of hydrogen atoms, and we know that these photons can then, in principle, contribute to the intensity at x. Right? So we have to take this into account in the Lyman-alpha scattering process. Right? So, basically, the reason this equation is so important is that when you think about Lyman-alpha, and we basically, in Masami's lectures, I think it also came up, interpreting Lyman-alpha observations is difficult because of the complicated scattering. That's entirely this term, right? So it's this simple term that basically complicates our interpretation of the observations. Right? So this is why I want to devote an entire lecture to this term here, right? This term on this reddish term. And so let me just say one thing. So this is actually quite a deep statement. Sorry, I already botched the joke a little bit, but in any case, this is quite a deep statement. So if you read this statement, the scattering process is fully encoded within the frequency redistribution term. That sounds pretty good. However, if Gendalf says it, it sounds even better, right? Sorry, I think it really does. Like, the scattering process is fully encoded within the frequency redistribution term in the radiative transfer equation. Okay, good. And this is a snowball, by the way, here. Okay, so our goal is now to understand this scattering term, right? So I would like to know R. What is R x out given x in? Right, and my next slide is going to be blank, and that's because I'm going to talk a little bit on the white and blackboard, actually. So I'm going to have to do a lot of walking. About some notation that is used in probability theory, right? And I'm actually not going to work that much with it in the lectures, but I still want to emphasize, I still want to discuss it briefly. So if you read the lecture notes later on, you'll have an easier time following the actual full derivation that is presented in these notes. And in this lecture, I don't have time to do the full derivation, but I can give you the brief steps. Right, so okay. So in probability theory, I'm going to use the whiteboard. I'm going to try to write as big as possible. I'm going to first. So the first thing I want to show you is, we're going to denote the probability distribution function p of x. That we're going to denote with just p of x, right? So this is the probability distribution function of x, or just the PDF, or the probability density function. Yep. Sorry? Do I have a black marker? Yes. So p of x, this is nothing special. So p of x is the PDF, the probability distribution function, or the probability density function, whatever you want to call it, right? So one example is, for example, here I've plotted p of h as a function of h. So the example here, h denotes my happiness, right? So generally speaking, this PDF looks a bit like this, where this would be very happy, so VH. And very unhappy would be something like, well, W, like whatever, So this is, generally speaking, the probability distribution of my happiness, right? The other thing that is important is not just the probability density function, but the conditional probability density function, right? So we have Px given n, for example, right? Or in this case, P of H, the happiness given n, right? So this is the notation we use for conditional probability. Now, conditional probability, n in this case, is that my happiness can depend on certain circumstances, right? So, for example, if we denote n with the number of snowballs I received in my face in the last 24 hours, then you can imagine that if n is very large, right, then the conditional probability that the conditional probability pH n very large would look something like this, right? I'll be much likely to be happy. So that's just a conditional probability. You can imagine that you can convert between the overall probability P of H and the conditional probability P of H by just summing over all possible number of snowballs I had in my face in the last 24 hours, right? So the two are related actually through a very simple equation, and sorry, I'm going to use the blackboard to do that. I don't have room for this. So you can imagine that, generally speaking, P of H would just be given by pH given n times the probability that I had n snowballs in my face, but then integrated over all possible n. Okay? So this would be your conditional and this would just be the total. Now there's one more quantity that we can introduce, and that's the joint probability. Right? You can you would want to know, for example, what is the probability that you're blah happy, H happy, and you had n snowballs in your face, right? So this one, you can imagine, this is again a different quantity than what I'm showing here. Right? This is just asking the question, what is the probability that you had n snowballs in your face and that you are this happy, right? So you can imagine that you can write this in two different ways. You can first say, okay, this must be simply proportional to the probability that I had n, times the probability that H. But we know that this probability depends on n, right? So we have to write it like this. At the same way, we can actually write this equation, the same equation, we could have started the other way around, right? We could have written P of H times P of n, but P of n could actually depend on happiness as well, right? The other way around. So this is just as generic as it can get, right? Now if you set these two equal, right, so we both know that these both are equal to the joint probability distribution of H and n. Right? So if we set these two equal, we get a very important inequality, and that's that my happiness, or let's say, you can actually calculate an interesting quantity, say, what is the probability that I had n snowballs in my face, given that I'm this happy, right? So you can calculate this probability suddenly, right? So that's this one. From these two equations, I can just immediately calculate it that this equals pH of n times P of n over P of H, right? And this is such a simple, one-line derivation basically, but this relation here is known as Bayes' theorem, right? And this is basically used, you'll probably use this a lot in, so Bayes' theorem. And in the lecture notes, it turns out that if you want to compute, for example, the redistribution function, you're going to be applying Bayes' theorem quite a few times. Right? I will not do it in detail in this lecture, but we will use it. Right. Okay. So to get some insight into this conditional probability, what for my outgoing frequency x out given my incoming frequency x in, right? We're first going to consider what we call partially coherent scattering, right? And partially coherent scattering is what usually applies in galaxies, in the ISM, and if you want to talk about Lyman-alpha scattering, or whenever we talk about it in our field, it's practically always partially coherent scattering. Now, what does it mean? It means that if you're in the frame of an atom, you look at the hydrogen atom, you transform into the frame of the atom, you're moving along with it. In the frame of the atom, the energy of the photon before and after scattering is identical. It's energy conservation. Right? Now, of course, the atom itself can move, right? So you have that's shown in this picture here. Right? So if the atom has some velocity, which it always has, right? When gas has a finite temperature, atoms will be moving. It has random motions. So because of the motion of the atom, actually the frequency will change with the scattering process. It will not be the same in the gas frame compared to while it stays the same in the atom frame. Right? And to see this, I'm going to actually I'm going to again do a calculation on the board, which is quite simple, but I think it is illuminating. And just to contrast this with other scattering processes, when you're, for example, in an extremely high density regime, right, when you have very frequent collisions between atoms, you can imagine that when your atom absorbs a Lyman-alpha photon, it's in a 2p state, it might actually collide with something else, and this is when you not necessarily conserve energy at all, right? And this is when people talk about, for example, completely incoherent scattering or something like that. So when people were writing papers on Lyman-alpha transfer in the 60s, 70s, etc., they were always considering this whole, all these different types of scenarios, right? And there's this other scenario which is called completely coherent scattering, which would correspond to a case in which you say, well, the atoms have no motion, which is a bit weird, but it would basically correspond to an ultra-cold gas. Right? So this is really the realistic case. So what we have to do is we have to continuously switch back and forth between the atom frame and the gas frame. Right? So I'm just saying, so gas cloud is moving at some velocity, we're sitting in the gas, but within that gas cloud, atoms themselves have thermal motions, right? So they're not the same frame. Okay, so we always express frequency of photons in this dimensionless unit x, right? So x, let's call it in the frame of the atom, we're going to call it x atom. And it equals the frequency of the photon in the frame of the gas modulo some Doppler boosting terms, right? So I'm just going to give you the result, and then we're going to talk about it. So this is just to compensate or to include this Doppler boost, this Doppler motion induced by the motion of the atoms. We just have to subtract, in this case, the velocity vector of the atom, the dot product with the propagation direction of the photon, this is a unit vector, over the thermal velocity of the gas. Right? And this term comes in because this dimensionless frequency units denotes the frequency offset in units of this thermal velocity. Right? So that's why this term is here. Right? So in other words, this is dimensionless. We have a velocity here, we must have a velocity here. Right? Otherwise it's not dimensionless anymore. Similarly, if we want to convert from the gas frame to the atom frame, we have the same expression, but we have a plus sign here, right? Okay. We know that in the atom frame, partially coherent scattering means that the frequency before and after scattering are identical, right? So we're going to start out with saying, what is the frequency of the photon after scattering in the gas frame? We're going to call this X gas out, right? Well, we know it's the frequency of the photon in the atom frame after scattering plus V dot K over the thermal velocity. But we know from partially coherent scattering that this equals the energy of the atom before scattering. So X atom out, we can replace that with X atom in. Oh, sorry. Plus V dot K over thermal velocity. But what is the frequency of the atom before scattering? In the frame of the frequency of the atom in the frame, the frequency of the photon in the frame of the atom before scattering. Well, that's equal to the frequency of the photon in the frame of the gas before scattering minus V. And in this case, it's K in, right? So it's the frequency of the photon it had before scattering. And for simplicity, or for clarity, we're talking here about the frequency of the photon after scattering. So this is the propagation of the photon after scattering, right? So same here, same here. This is what I wanted to get at, right? So you basically have now related the frequency of the atom, of the photon after scattering, to the frequency of the photon before scattering, simply through some the propagation direction of the photon before and after scattering, and the velocity of the atom. Right? So these are the terms, the only things that matter. Right. So this is what I just derived. Now, one quick comment. An effect that turns out to be not important in most of our applications at all, unless you want to do, for example, when I'm going to talk about 21 centimeter, the following effect is going to be important. Right, I told you that the energy before and after scattering are the same in the frame of the atom. That's not entirely true. And it's because a photon carries momentum. Right? So you can imagine, suppose you're sitting in the frame of the atom, so the atom is just sitting here. Photon comes in, boom, bounces off in this direction. If that happens, you know that momentum is not conserved, right? Because the photon carries momentum, that's pointing in this direction. If it were going in this direction after scattering, there would be no momentum left in this direction after scattering. So we would violate momentum conservation, right? Oh. Now basically to guarantee momentum conservation, we know that the atom actually itself must get a little kick, must be pushed a little bit by the photon itself. Right? And in this case, for example, it turns out that your photon comes in, it bounces this way, the hydrogen atom gets a small push in this direction. And a collaborator of mine once pointed this out as having you should see this as having a whole bunch of, I guess, trucks sitting in a parking lot, and there's small tennis balls bouncing back and forth between them, exerting pressure on these trucks. Right? So there is some transfer of energy from the photons to the hydrogen atom in this case. And so people have, for example, worried about this, that this might actually heat the IgM, that Lyman-alpha scattering in the early universe might heat the intergalactic medium because of this process. That turns out to be not so important, but it's something that happens. For the Lyman-alpha transfer that we're going to discuss in galaxies, this effect is never important. Right? So, and what it does, it adds a small corrective term to this relation that we just derived. That's just for completeness. Right. So what we would like to do is, now that we have this, right? Now that we have this expression, and recoil is included for completeness, but we might as well ignore it. The frequency change of the atom before and after scattering is determined entirely by the atom's velocity, this v here, right? And here, and k in and k out, or the angle between the two, the scattering angle, right? Because I can just, in principle, I can just pick any direction for the incoming photon, right? And what matters is basically the change, how k out differs from k in. So this scattering angle, this is basically the second ingredient that enters. Now this scattering angle, that's what we talked about this morning. The scattering angle is something that is determined entirely by the phase function, right? And we derived this morning that for dipole scattering, or for like a free electron, this phase function looks like this: 3/4 times 1 plus mu squared. And mu was cosine theta, right? So the angle between incoming and outgoing direction. Phase function for isotropic scattering is just a constant. You're equally likely to scatter in all directions. And for Lyman-alpha scattering, it was the superposition of these two. And so we know the probability distribution function of given a photon is coming in this direction, we know exactly what the distribution of outgoing angles is. So we know what this mu, this angle is determined by. Right? It's entirely quantum mechanics. It has nothing to do with anything else. So we basically know where this is coming from. This is drawn from a distribution given by the superposition of these two terms. Now once we have this scattering angle, we have the incoming frequency of the incoming photon, we have the scattering angle, we basically now know, when we almost have everything we need to compute the outgoing direction if we have the photon's velocity. Right? The atom's velocity, I mean. Now if we want to compute this, the trick is then, this is still a probability distribution function for x out, right? So what does the distribution of x out look like given x in and the scattering angle? As this is what we would like to know. So from this, I'm not going to go through the analysis in detail, but from this, just from this, we know that we have x in, we specify mu. What determines the likelihood of having some frequency x out is entirely given by the likelihood of having some particular set of atoms' velocities. Right? So the way I think about it is, or the way you should think about it is that the atoms' velocities have three components, right? An x, y, and z components. Right? They can in principle take on arbitrary values, right? With some probability distribution function given by the Maxwellian distribution for gas at that particular temperature. Right? Now you can see a certain subset of all these values for these components will give you, for a given combination of mu and x in, will give you x out. Now if that parameter combination is very unlikely, then you're very unlikely to come out at this particular frequency. Right. So that's, and in the lecture notes I'm actually going to go, I'm going to walk through the entire derivation, and it would involve integrating basically over all possible combinations of atoms' velocities and see how unlikely these are. Right? And this involves this Bayes theorem that I derived earlier. Applying that over and over again is just bookkeeping. But once you do that, in principle, you can compute exactly what the likelihood is that x out is coming out at this particular frequency, given this frequency before scattering and the scattering angle. And I'm just going to show you some results. Right? So this would be an example. This is the probability distribution function that the outgoing frequency of the photon has a value x out, given the incoming frequency, in this case x is 0, right? So exactly at line center, and mu. And in this case, mu is minus 1/2. So that means that the photon came in like this and scattered like this. Right? It's scattered back. Now for x is 0, you sort of see that the distribution of outgoing frequencies is sort of, it's almost like a Gaussian. The frequency of the photon doesn't change very much. Like for x is minus 3, it looks really weird. Right? It looks like a strange double-peaked thing. And you can actually understand that without going through the math. I mean, in this case, the frequency of the atom before scattering was minus 3 in these dimensionless units. That means that the frequency was a bit below the Lyman-alpha resonance. It had a lower frequency, lower energy. If it had a lower energy, the photon was moving in this direction with a lower energy. Atoms that were just sitting still would see a photon with a lower energy. Right? And they would be a bit less likely to absorb it because this photon would appear far in the wings of this Lorentzian profile in the frame of that particular atom. However, you have some atoms that are moving in this direction, and for these atoms, the photons appear much closer. The photon appears much closer to resonance, so it's much more likely to absorb it. Right? So in this case, if you have your atom is moving into the photon, it looks exactly at resonance, right? And then it scatters the photon back in this direction. So it's almost like the photon is moving this direction, the atom is coming in and boom, bounces it back in this direction, and it gains energy. So that's why suddenly there's a pretty large probability that this atom has now a positive energy, or a positive frequency compared to the resonance frequency. And so it has gained a lot in this particular encounter. This particular hump here is just from those atoms that were actually sitting still and sort of absorbed it at a lower frequency and then randomly re-radiated in another direction. I will not discuss this one. But just to show you the directional dependence of this thing, this is from mu is 0.5 here. This is from mu is 0.5. It looks completely different. Right? So this is minus 5.5, minus 5.5. Right, so the directional dependence is there. And what we want to do is, we are interested in, ultimately, this is what we were interested in. Right, we want to know x out given x in. Right, so now we have to apply one of these one of these rules of statistics that I mentioned on the board earlier, right, is that your conditional probability given mu, you have to integrate over all mu basically. Right? So in this case, mu takes on the number of snowballs, right, that I had in my face, and you just integrate over the probability that mu takes on a certain value. Now this is for isotropic, so it's a constant, so you don't see this term. This is for dipole scattering, so it has the 1 plus mu squared. Right? Now this is what these functions look like. And this is what people focused on in the I guess 70s even and before that. Right? They were computing these redistribution functions. Right? And the red lines here are for isotropic, so that will be Ra. And the dashed lines or the dotted lines are for dipole scattering. And we know that true Lyman-alpha scattering is somewhere in between these two cases. It's a superposition of these two, so it's somewhere in between. But in practice, it doesn't really matter. The difference, it's so close that it doesn't really matter which you choose. Okay. Right, so now there's one thing that once you have specified, so you can actually, the point is, you can compute all these redistribution functions. Right? You can plot them up like this. And what you can then do is you can also look at some properties of them. Right? And the first, I think, one of the most important, possibly the most, well, there's two most important properties of this redistribution function. The first one is this. It turns out that if you have a photon coming in at some frequency x in, right, and you ask yourself, what is the probability, what is the most likely change or the average change in photon energy or frequency change in a single scattering event? Right? If you average over all scattering events, it turns out that it's equal to 1 minus xn, xin, 1 over xn. Right? And what this means is that, suppose you are a photon that is very far from the wing, but at a very high frequency, the scattering sort of tends to push you back to line center. Right? If you're very far in the wing on the low energy side or the low frequency side, again you get pushed back to the center. Right? So what that means is that your photons are sort of scattering, they change frequency, but once they're away from resonance, sort of nature tries to get them back. They want to pull these photons back to resonance. Right? And the reason for this, there is an intuitive way to see this, and that is, if you have, say in this case, an energy, a Lyman-alpha photon that is redshifted, so I've drawn it in red here, it's redshifted, lower frequency, it turns out that atoms that are moving into the photon are somewhat more likely to absorb them than atoms that are moving away from them. And that's because for these atoms, these photons actually look closer to resonance. Right? So they're more likely to be absorbed by atoms that are moving this direction than atoms that are moving this direction. Now, if that's the case, and we've showed in this previous plot that atoms that move in this direction, in the frame of those atoms, the photons have higher energy. They're scattered according to either dipole or isotropically. They end up with a slightly higher energy on average. And it's tiny, the effect, but it's very important. And why this is important will become apparent tomorrow. The other thing that is important is that you can ask what is the root mean square change in the frequency with scattering, right? And that turns out to be 1, right? So the RMS change between x in and x out is of order 1. Right? So what that means is that you have a photon, every time it scatters, there's a small change to the frequency. Now we know that the change to the frequency is, what that does is it makes a change to the cross-section, right? Because the cross-section is so strongly frequency dependent. A change to the frequency is a change to the cross-section, is a change to the mean free path of the photon. So what that means is this, right? So the movie that I showed at the beginning of my presentation, right, shows you actually a real simulated mean free path of a Lyman-alpha photon. Right? So this is actually, has the proper frequency redistribution in it, it has the proper phase functions, etc. Now the color is related to the frequency of the photon. It's a bit weird. But the main point here is that you see this random walk, right? This photon is bouncing around. But it's not, you can see it's not the mean free path of each, the mean free path can change drastically each time it's after each scattering event, right? And that's because of this, every time you scatter, you change the frequency slightly. So for example, this long line here, the photon was sort of scattered to a frequency that was a bit further away from resonance. So that's why the mean free path goes up. But in this case, what you also see is that, the mean free path, generally, you have these excursions, like between here, and then the photon sort of bounces around again. So that's again a consequence of the fact that you have these photons. Once they're scattered into the wing, nature wants to pull them back to line center, right, where the mean free path is shorter. And so, and this is scattering in a uniform medium, right? So this is just a uniform gas cloud, and this is a representative mean free path of a Lyman-alpha photon through such a medium. And this movie goes on for 3 minutes, so.
Is that a screensaver?
I actually don't know, it's not. But this is a snowball. Now this is not a screensaver, but if you want, you can get it.
That would be a great screensaver.
The interesting thing is that this, I'm not actually, I have to look up the number of scattering events that is, the number of scattering events in this case. Yeah, thanks. The number of scattering events here is, it's not clear to me what actually, I have to look that up, what the largest displacement is, or what the largest change in frequency is actually here. Now what we'll see tomorrow is that if you have a medium like this, you can imagine that once you are in a regime where you can make these large jumps, right, it becomes more easy to escape. Right? Okay. Actually, I think that was it. For frequency redistribution, I'm done. What I can briefly tell you before, you can ask you can ask questions anytime. But what I'll briefly mention is that what I'll begin with tomorrow is that these two properties here, this one, and also this one, I didn't place much emphasis on this. It's not. The only reason this one is important is that it allows us to rewrite the radiative transfer equation describing the scattering in a very convenient way, right? And what we'll actually, I'm not going to show it in detail tomorrow, but I'll mention it, right? We had this complex integral differential equation which was shown here, right? This one, and it's complex because you're really mixing in frequencies. You want to evaluate the intensity at some frequency x, but you're really mixing in with the scattering process. You're bringing in the intensity at other frequencies x prime, and you have to understand all of them, right? So you have to sort of solve for the intensity at all frequencies at the same time. So if you want to do this analytically, it's very complex. However, what we will find, what it turns out that with the properties of this redistribution function, you can actually simplify this equation into a differential equation, a pure differential equation, which looks exactly like a diffusion equation, right? And so which is good because you no longer have a integral differential equation, but you have a diffusion equation. And it's not strange that this process is described by diffusion, because if you look at this movie again, you sort of can see that the Lyman-alpha transfer is kind of like a diffusion process in which Lyman-alpha photon just randomly bounces around, right? It's randomly bouncing around like diffusion. But in this case, diffusion is a bit weird because the mean free path is changing. And it turns out that the diffusion process is unique in the sense that it's a double diffusion process. You're not just diffusing in real space, like in this picture, but you're also sort of diffusing in frequency space. Right? If we were to wait longer and longer, the probability that one of these photons would encounter a hydrogen atom that will be moving very fast, it stays the same. But as you scatter more and more, there will be a time at some point where you meet an atom that was moving absurdly fast. And then in that case, you could actually scatter much further into the wing of the line, and your mean free path would sort of, could actually easily be larger than this building, right? Now, and once that happens, then there's still a tendency for the photon to be pushed back to line center. But if you are sufficiently far away in the wing of the line, you can imagine that the amount that you get pushed back by is only minus 1 over the frequency offset, right? So the further you are away from line center, the harder it actually gets for nature to push you back. Right? So you might have a very long mean free path, you might have another one then, and another one, and another one, and another one, and after a number of scattering events, you sort of return to the core, you start repeating this endless number of scattering events, apparently. But yeah, so this is, so we'll talk about that more later, but if you have any questions about this, then this would be a good time. Yeah, please, yeah.
So how does Lyman-alpha end up escaping then? I guess sort of broadly, particularly if it's always trying to be forced back to line center in sort of astrophysical conditions, is one of these sort of, well, I guess without being destroyed. Because I mean, yeah, this is the first time that I've sort of seen this and been like, oh, it is much less probable than I sort of imagined.
Well, I mean, okay, so this is a static homogeneous medium, right? So it will still escape. I mean, like the tendency to be pushed back into line center becomes less as you move further away into the wing, right? So there are, and even though the probability that you get scattered far into the wing, say to x is 20 or something like that, are very small, it's not negligible. So it will happen at some point, right? And once you're there, you're going to stay there quite a long time before you return to the core. So you can actually scatter quite a few times in the wing of the line with this large mean free path. And we actually call that process in which you scatter far in the wing of the line profile. Repeated scatterings far in the wing, we call that an excursion. Right? So you can escape in an excursion. Right? And, but this is still idealized, right? In real galaxies, this will likely, something like this process with, say, 1,000 scattering events will probably happen in H2 regions, right, where the optical depth is 10 to the 4. So this will likely happen. However, you also have gas motions in galaxies, and you have, I guess, holes and stuff like that. And this also sort of tends to facilitate escape, right? If you have a gas clump moving with a very large velocity, you can imagine that sort of acts almost like a single atom moving at a very large velocity, so you get really efficiently bumped into the wing of the lines. Right? You had a question as well.
What does the color now actually represent?
Yeah.
So it's not the frequency, right?
No, sorry, that's a good question, and maybe I should have used another movie for that. So there was something. I think the color sort of does represent the frequency of the photon after it scatters. But then I think the coloring scheme is sort of then changing. I'm not sure why it is actually. It is a numerical thing, right? So it's I should have, yeah. I think it makes for a better screensaver that way. I mean, but to be fair, like the frequency of the photon doesn't change. It should not change, right, during flight. So it does actually in the IGM, right? If you have a photon scattering in the IGM, it could be that the Hubble expansion changes the frequency, but that's not. Right, yeah, exactly. So it's the Hubble contraction, right? Yeah, Martin.
If your expectation is, so delta x is minus 1 over x in.
Yeah.
But if your x in is then very small, does it mean it also gets pushed towards the wings?
No, that's a good question. Yeah, so I'm just going to keep this because I like this movie, okay? Now, so that particular approximation, that property, it turns out, in the very beginning of the presentation, I was sort of saying I'm going to assume the radiation field is isotropic, I'm going to, right, that's only the case, so in optically thick media, etc. But this particular derivation is only valid if you're far in the wing of the line profile. And so that's the approximation that you make once you have this particular form.
So if x in is small, it's not that
Right.
is not exact.
Let me actually show you. So for example, you can actually see it a little bit here, right? Here you see x is 4, so that's already in the wing of the line. I don't know how good your eyes are, but this is slightly asymmetric, this function already, right? And it's sort of skewed back to 0. But you can see that at x is 0, for example, right? It's sort of the expectation value is not minus 1 over 0, right? So that's it. Just that this expectation in the change of the photon only is only valid once you are far away from line center, and it sort of becomes valid at x greater than 4 absolute value, right? So here I'm not so sure if it's valid or not. It looks, yeah. It looks still, it's still, yeah. I just don't know, yeah, when it becomes valid exactly.
No more questions. Just thank you.